Okay, so this physics problem dealing with some circuitry, energy, and work questions, I think is a pretty good unifier between Physics 1 and Physics 2 concepts. So hopefully that was a good reminder of some of those terminologies and things. So first, we were given a motor that uses a certain amount of current and has a certain amount of potential difference across it, and we have to figure out the power supplied to the motor. So if we look on the equation sheet, we see for circuitry, the definition of power is I delta V, right? And so we just plug those numbers in, 1.0 milliamps and 3.0 volts gives us a power of 3 milliwatts, right? Remembering the units for power is important. So you have to remember that power is in units of watts. All right, so that's part A. That's the power that we supply to the motor. Part B is really straightforward if you remember the definition of power in general, right? Power, by definition, is sort of the rate that energy is given to something, or the rate of work that is done, or something like that. It's amount of energy per time. So we know power, and we're told at 60 seconds, we want to figure out the total amount of energy. So delta E, the total amount of energy that the motor uses, is power times delta T, which is 3 milliwatts times 60 seconds, right? And if you plug that in, you get 0.180 joules, right? That's the energy. Okay, so parts A and B are fairly straightforward, pretty fast calculations. Just remember what the units and definitions of power, energy, and how that relates to circuitry. Part C is not something that I would expect the AP test to ask you as much anymore without giving you a more detailed definition of the text. But I think it's a useful concept, so I left it in there. It's definitely something that you can understand conceptually. So the idea of efficiency is something about like how much useful energy comes out of something per the amount of total energy you put into it. So, for example, something with 100% efficiency, every bit of energy you put into it goes into doing what you want. So if you make a motor that lifts boxes, if you put 100 joules of energy in, 100 joules of energy go into moving boxes. Something that's very inefficient, you might put like 100 joules of energy into it, and only 10 joules go into actually lifting a box, and the other 90 joules go into like moving pieces inside the machine, or loss to friction, or who knows what. So efficiency is a measure of sort of how much energy you put in relative, or sorry, how much energy you get out that's useful relative to how much energy you put in. So, our useful out energy is the energy of lifting that box, right? That's what the motor is trying to do. So that's like, so our energy that's going out involves lifting a box. And we can calculate that as like the delta U gravitational energy of the mass, right? Because it's at constant velocity. So the energy that goes out of the motor that goes into lifting the box, it's useful, is the change in potential energy of the box, which is mgh, which is 0.012, 1.0 meters, and 9.8 meters per second, right? Which is 0.12 joules. That's the useful energy that I get out. Well, how much energy did I put in? That's 0.180 joules. It's whatever you got in the previous part, right? That's the amount of electrical energy the motor uses. And so then the efficiency is 0.12 over 0.18, right? Is 66.7%, or 0.667, right? Again, not the most critical part, but a concept of efficiency I think is kind of a useful practical thing. Okay? All right, so this last part, we have to figure out how we make a circuit that does this. Right? So we have our motor, with two ends to attach it to, and we have our battery, 9 volts. So the first thing I recognize that if my motor is set up with these constraints, we can assume that it's roughly ohmic. So we can apply Ohm's law and find that the resistance of the motor to have a 3 volt potential difference across it when it's running with 1 milliamp of current through it must be 3,000 ohms. Okay? So now we want a circuit where we need a total potential difference of 9 volts. And we need 3 volts of that over this motor. And we have 3,000 ohms of resistance already in our circuit. So we need to figure out how to get an additional, so somewhere in here, right, somewhere in here we need delta V equals 6 volts, right? That way we can satisfy Kirchhoff's law. And if we need 1 milliamp of current, then R must be 6 volts over 1.0 milliamps. So whatever we put in there needs to have a total resistance of 6,000 ohms. So I look at my list of resistors, and I see that I have two 4,000s, a 5,000, a 1,000, and a 10,000. So the 10,000 is not useful until I do like a parallel combination. But all I really want to do is get to 6,000, and I notice that 1,000 plus 5,000 will give me that. Right, so if I connect this like that, and then there, and this is 1,000 ohms, and this is 5,000 ohms, then I will satisfy those rules, right? Delta V on the stuff that's not the motor will be 6 volts because it has a total resistance of 6,000 ohms. So the motor will get its correct voltage and potential difference, right? So something in series.